Okay, now I will present you the characterization of a lens. Here it is a doublet with a focal length of about 400 millimeters and a diameter of 50 millimeters. And I'm going to characterize it in double pass with a R-FLEX sphere here. And the R-FLEX sphere is a combination of the source that is collimated here. The source is 1550 nanometers in the sphere. And then there is here an objective in order to adapt the numerical aperture to the lens we want to measure. So the light is focalized at the focal length of this lens, and then the light is collimated by this lens on this mirror. It's coming back, and the light and the aberration are measured by the HASO4 sphere here. I have pre-aligned everything, but it's very easy thanks to these rotation stages. And let's have a look on the result. And as you can see here, I'm not already perfectly aligned because I have some residual tilts and some curvature. So I will reduce the tilts. First of all, the tilt on the x-axis to be as close as 0 as possible. Here we are. And the same for the y-axis. Yes, now we are very close to 0. And as you can see, the curvature is not perfectly at infinity. So I will reduce the curvature at 0 in order to have a perfectly collimated beam on the wavefront sensor. That means that we are exactly in a double pass configuration with a collimated light here, a collimated beam at the outside of the lens, and that means that we are measuring in the focal length, focal plane to infinity configuration. So here we are, and what we can see on the screen, we do have here the wavelength, the aberration, and we have here the decomposition of this aberration on the Wernicke polynomials. And as you can see, we do have mainly some spherical aberrations. So what can we do with this aberration? We can calculate, first of all, the PSF. And the PSF is this one. I can zoom in order for you to see pretty well. So we do have a quite good PSF because we have reasonable aberrations. And thanks to this PSF, we can calculate the MTF. And here we do have the MTF. And as the aberrations are relatively small, the MTF is not so bad. And you can see here this PSF compared to the theoretical with absolutely no aberration PSF here. We do have the result on two different azimuths for 0 degree and 90 degree, but we can for sure change the orientation in order to have the full 3D PSF. So that means the PSF in all directions, all azimuths. So here, with this R-FLEX sphere, we can have the characterization, the full characterization of this lens in terms of aberrations, PSF, and MTF. And as you have seen, it's really simple to get this characterization. For sure, if you have an objective lens with a different numerical aperture, a bigger or smaller one, we can adapt, and we have a long range of different objectives here to adapt to different numerical aperture.